Okay, molar mass of a gas. So the idea here is we're going to release gas into an inverted graduated cylinder, and then through downward displacement, that gas is going to occupy a certain amount of space at a certain pressure. And based on the mass of the gas that's occupying that much space, we can figure out what the molar mass of that gas must be. So here's our beaker filled with water, and then we have a graduated cylinder that would initially be completely full of water. Then we release some gas bubbles into it, and that gas would push out some of the water and occupy a certain amount of volume up here. You might recall from an earlier video that we did on Dalton's law of partial pressure that some of this gas in this region is going to be the gas of interest, but we're going to have a secondary problem here, and that is vapor pressure. So what do we have? It says that it was a mass of 0.24 grams of the gas that was released. The temperature is 23 degrees Celsius, or if we add plus 273, we can say it's 296 Kelvin. We'll need that for calculations. The pressure is 100 kilopascals. We're assuming that's the air pressure that's pushing down, and so if this is pushing against it, they would be the same. And it's going to occupy a volume of 0.035 milliliter, or 35 milliliters, or 0.035 liters. So the question is, with this pressure here, how much is the pressure from the gas that we're interested in? How much is vapor pressure? To figure that out, we have to go back to our chart of vapor pressure. And this vapor pressure is given in torr, which is a little annoying, but at 23 degrees, we see we have 21.1 torr. So if my temperature is 23 degrees, then my vapor pressure, no, I forget the number. What was it? 21.1? Yeah, 21.1 is 21.1 torr. Keeping in mind that for every atmosphere of pressure, 101.3 kilopascals, we're talking about 760 torr. So if I want to convert that, 21.1 times 101.3 divided by 760, I would get that it is 2.8 kilopascals of vapor pressure. So if I have my total pressure, that consists of pressure from, we'll say, gas X and pressure from the water, or H2O. So if my total pressure is 100 kilopascals, then that is a combination of my gas of interest plus water at 2.8 kilopascals, meaning my gas of interest is 97.2 kilopascals of that total pressure. Now I have my mass. I have my temperature, pressure, and volume, so I can come up with my moles. And if I have my mass and my moles, then I'll just be missing my molar mass. So to come up with my moles, I'm going to use PV equals nRT, since I'm not working at standard temperature or pressure. 97.2 kilopascals, 0.035 liters, 35 liters. Moles is what I'm looking for. I can use 8.31 because I'm in kilopascals and liters. And my temperature of 296 Kelvin. Okay, so 97.2 times 0.0352, 3.42 on this side. 296 times 8.31. 2,460 over here. So I end up with 0.00139 moles. Okay, so moles is equal to mass over molar mass. My moles is 0.00139. My mass is given here at 0.24 grams. And so all I'm missing is my molar mass. So molar mass is equal to 0.24 grams divided by 0.00139 moles, which means the molar mass of this particular gas would be 172.6 grams per mole. So again, I took some sort of graduated cylinder, I released gas into it. That gas, along with water vapor, occupied a certain volume. I took out the pressure of the water vapor using a water vapor chart. I saw what pressure was left over. I used my pressure, volume, and temperature to predict moles. Given my mass and my moles, I was able to isolate for my molar mass.